Hi, everybody. We are moving into a 3-module section on Greek mathematics. And there's so much about Greek mathematics, we could actually do the whole course on that, probably several courses. In fact, I know that because the middle one is on Euclid's elements, and there are lots of universities that have courses on Euclid's elements, Euclidean geometry at the university level. So today what we're going to talk about in this module is the Greek mathematics before Euclid. And again, there was so much there, I had to do some picking and choosing. So we're going to talk about the work of 3 mathematicians, all of whom also had a philosophy bent to them. So frequently in ancient mathematics and ancient science, the people that we're talking about had more than one job, or they wore more than one hat. And a lot of times the mathematics were also philosophers. So you'll see that not just at this time, but throughout the 20th century as well. So we're going to start off talking about the ancient Greeks, and I'm only going to use the PowerPoint just a little bit, but make sure you do go work through that PowerPoint, watch, listen. No, there's nothing to listen, but watch and read the PowerPoint because there is some more information there. The first mathematician that we're going to talk about is Thales, Thales. Thales is known as the first mathematician that we've got any information about, and we don't have a whole lot of information about him. You know, it may be that there were other mathematicians before him, we just don't know about them. So Thales is the first person that we've got information on that somebody else wrote about what he did. We don't have his actual writings, any documents, any pamphlets, any books that he wrote, but we know that he existed. We know of his work from other people who wrote about him. And what we know about him mainly is that he came up with these 5 theorems, and here they are. Come on, focus. We don't have any proofs, any of his proofs of the theorems, but we do have the statements of these theorems that are attributed to him. The first one is a circle is bisected by any diameter. And you may think that sounds like a kind of strange theorem, but it is a theorem depending on how you define a circle and a diameter. If you define a circle as a set of points that are equidistant from a given point, and that given point that you're talking about is the center of the circle, there's your definition of the circle. If a diameter is any line segment that goes through the center of the circle and intersects the circle in 2 places, there you've got a definition of a diameter. But that doesn't say that that diameter divides that circle into 2 pieces. It just says that it goes through the center and it hits it over here and it hits it over here. That's what the definition is. So if that's your definition, then yeah, I do need a theorem that tells me what exactly the diameter does. Why is it important? This is a familiar theorem to us. The base angles of an isosceles triangle are equal. And notice we're using the word equal here. That was typical back in the day rather than using the word congruent. Congruent is a fairly new idea. The idea that 2 geometric shapes are congruent means that if you could slide one on top of the other, they would match up perfectly. So we talk about geometric shapes are congruent. We talk about numbers today are equal. So just keep that in mind as we look at the work of Thales and in particular Euclid. I'll bring that up again. Vertical angles formed by 2 intersecting straight lines are equal. That's one of the first theorems that we learn in geometry. 2 triangles are congruent if 2 angles and a side in one triangle, and he didn't use the word triangle, but in one, talking about triangles there, are equal respectively to 2 angles and the corresponding side of the other. Two triangles are congruent if 2 angles and a side. There you go. So I've got 2 angles and a side. Notice this doesn't say that the side has to be between those 2 angles. So this theorem has a lot packed into it. It actually has 2 separate theorems that we look at today, usually in geometry. We would look at the angle side angle theorem, where the side is between the 2 angles. And then once we know that the 3 angles of a triangle add up to 180 degrees, we know that if we've got 2 angles congruent to 2 angles of another triangle, all 3 are the same. So then no matter what that side is, it's between the other two. So that would give us the angle side theorem. This one might be one that's not quite as familiar to you, or I'm sure you used it. It's just been a long time since you did something with circles. An angle inscribed in a semicircle is a right angle. So what that means is that I've got this semicircle. Let me draw in this diameter. And so the top half of that is my semicircle. An angle inscribed in that semicircle has its vertex on the semicircle. So there's the vertex, and I'm going to draw the other two sides of the angle so that they intersect at those endpoints of the diameter. And what this theorem tells me is that this has to be a right angle. Now that's true no matter where I happen to draw my angle. So over here, same thing, draw in the two sides of the angle so that, no, don't go through the center, so that they go through the opposite ends of the diameter. That right there would be a right angle. And each of those two angles is inscribed in the semicircle, right? There's the semicircle. The vertices of both angles are on the circle, and the legs of the angles go through the ends of that diameter. Okay, so that's Thales. We've actually got from people who wrote after him about some of the typical kinds of problems that he did. He did a lot where he was using similar triangles. So those would have been typical problem types for Thales, the first mathematician that we know about, who happened to be primarily a geometer. Zeno is another person who dabbled in mathematics and also philosophy. And we know Zeno from a lot of his paradoxes. And there are many of those. I have only chosen Achilles and the tortoise. So Achilles and the tortoise are going to run a race. And we're going to say, here's the racetrack. Here's Achilles up here. Here's the tortoise down here. They're going to start here at the same place, and they're both going to run in the same direction towards the finish line over here. All right. Now here's the deal. Achilles knows that the tortoise is really slow. So he's going to give that tortoise a head start. And let's say that's 11 and a half. So about 5 3/4 is about halfway through. That's about halfway through. When the tortoise reaches this midpoint, half of the way to the finish line, Achilles will start to run. Okay, so Achilles starts to run. The tortoise is right here. Achilles has run to here. But by the time Achilles gets to where the tortoise was when he started, the tortoise has moved ahead some. Maybe the tortoise is there. So the tortoise at this moment in time, Achilles is at the midpoint. The tortoise has moved ahead. So they're still both moving in this direction. Nobody's stopping. I just kind of did a stop action to talk about it. So they both keep running. And by the time Achilles gets to where the tortoise was, the tortoise has continued to move. He's moved on ahead so that when Achilles is right here, maybe the tortoise is right here. And when Achilles reaches this point, the tortoise has moved ahead. So the tortoise is still ahead of Achilles. When Achilles catches up with him, well, the tortoise has moved ahead. The paradox is that it seems like the tortoise is always ahead. Is the tortoise always ahead of Achilles? Well, we know in real life that the answer is no. Achilles is going to beat the tortoise to the finish line, unless we've set the finish line so far ahead and we've let Achilles run so slowly that the tortoise is going to beat him. Unless we've rigged it in some way, Achilles is going to beat him to the finish line. So what's the deal here? Well, let's look at it mathematically. All right, mathematically, how far do they each run? Okay, and I'm going to say that the length of this race, the length of this course is 1 unit. So I can talk about this distance is a half, and then 3/4, and then a fourth more, and then an eighth more, and so on. So how far do they each run? Well, they each run half of the course. And then they run another, then they take half of the half. So they run another fourth. And there's a fourth left. So half of that is an eighth, and then a 16th, and so on and so on. So that seems to be the distance that they're running. Half of the course plus a fourth of the course plus an eighth plus a 16th plus, and so on. So what's the deal here? It appears that they're both running the same distance. And by the way, this would be the entire course. So this infinite series should add up to the entire course, should add up to 1. But it appears that they're either never going to reach there because they're always moving. That doesn't make sense. It also doesn't make sense that Achilles is already behind. Well, the math behind this deals with the convergence of an infinite series. And you learn in calculus that this series does converge. This series does converge, and it converges to 1. So another way to think about it is, suppose Achilles is going 10 miles an hour. That's a 6-minute mile. That he's a good runner. All right, Achilles is going 10 miles an hour. And so he's going to run a mile. Let's say this is a mile. So if he's running 10 miles an hour, then it's going to take him, what, 6 minutes to get there? All right, well, a good question would be, here's a problem for you to think about. How fast does the tortoise have to be running so that he and Achilles are going to cross the finish line at the same point? Now, I doubt seriously that this tortoise is running 10 miles an hour. So he's slower than Achilles. I don't know what the typical speed is of a tortoise. We could go look that up. But the question right now is for you to think about. I'm not going to tell you this. How fast would the tortoise be running so that he and Achilles would cross the finish line at the same point? Well, once we figure that out, we know that if the tortoise is running faster than that, he would beat Achilles. If he's running any slower than that, Achilles is going to beat him. But the paradox here is, first of all, is the tortoise really always ahead of Achilles? And then second of all, if you think about it again, do they ever, either of them, reach the finish line? Mathematically, yes, they do. Achilles is going to win, assuming he's running enough faster than the tortoise to win the race. Achilles is going to win. They both finish the race. And the sum of this infinite series is equal to 1. Okay? It's a calculus problem. No wonder Zeno didn't have an answer to the paradox. No wonder the other mathematicians didn't. No wonder they didn't have a good answer for this for years. They needed calculus. They needed infinite series. They needed the idea of convergence to be able to really make sense out of this. Okay, we're going to move on. There are 3 famous problems from ancient Greece, known as the 3 problems of antiquity, or the 3 ancient problems of mathematics. And we're going to look at each one of these. Squaring the circle. The problem is it possible to construct a square whose area is the same as a given circle? So you're given a circle. We start with this circle whose radius is r, and I'm looking at areas. All right, the area of the, we're going to use some stuff that we know. The area of this circle is pi r squared. And what I want to do is construct a square over here whose side length is x. The area of the square is x squared, and I want these two areas to be the same. I want the area of the circle to equal the area of the square. So I need pi r squared to equal x squared. All right, now I'm trying to draw this circle. So that means what I need to, I'm trying to draw the square. So what I need to do is solve for x. So if I take the square root of both sides, I'll get x equals the square root of pi r squared, which is the square root of pi times r. So it boils down to, what about this square root of pi? There's r. I can create a line segment whose length is r or 2r or 1/2 of r, 1/3 of r, but I need one that's the square root of pi times r. Well, as it turns out, the square root of pi is not a constructible number. The square root of pi is not a constructible number. But this was not proved until the 17 or 1800s. So for a couple of thousand years, mathematicians worked on this problem, trying to figure out a way. Now, I forgot to mention this. The only tools that we can use are a compass. This is important. And a straight edge. For all three of these problems, these are the only two tools that we can use. So using a compass, which means I can only draw a circle, draw a straight line segment. That's all I can do. But there's a ton of stuff I can do with those two tools. Lots of constructions I can make. Could I make this construction? Well, the answer is no. But mathematicians didn't know that for several thousand years, and they continued to work on this problem. What happened is that as mathematicians worked on this problem, sometimes they thought they had it. I've got it. I've solved the problem. Well, somebody else came along and looked at it and said, no, you didn't. You did something here that was against the rules. You didn't just use a straight edge, the straight edge of this ruler. You used the edge of the ruler where you were measuring something. Typically, that's the mistake that people made. So, or they used a tool other than these two right here. A lot of good mathematics came out of attempting to solve this unsolvable problem using just these two tools. Okay, well, let's go to the second one. The second one says, is it possible to construct a cube whose volume is twice that of a given cube? All right, so I'm starting with a cube. And here's my cube. There's my cube. And I know what the volume of this cube is. This is the one that's given. So let's say the side length of this cube is x. The volume of this cube is x to the third. I want to figure out, or what I want is a second cube. It's got to be bigger, right? A second cube that's bigger. And let's call its side length y. So its volume is y to the third, but I want this volume to be twice this one. So what I want y cubed to be twice as big as x to the third. So let's solve this equation for y. I want y to be, take the cube root of both sides, the cube root of 2 times x. Well, I've got x. I would just take my compass and I would open it up so that I can measure how long that is, come over here, and I can draw a straight line of the same length. But can I draw a side length? Can I draw a line segment, which is that length times the cube root of 2? Well, as it turns out, the cube root of 2 is not constructible, which means you can't draw a side length. You can't draw a line segment with that length using just a compass and a straight edge. And since I can't draw that line segment, I can't draw that product right there. Well, again, here's another problem that's unsolvable using those two tools, but mathematicians worked on it for thousands of years. And again, lots of good mathematics came out of it. At some point, they were doing some pretty sophisticated mathematics working on this problem, solving it using sophisticated methods other than a compass and a straight edge. Trisecting an angle may be the one that's the most familiar to you. The idea here is that you can take any angle, any angle whose side length is theta, I'm sorry, whose measure is theta. And what I want to do is divide this up so that that length right, or that measure right there, would be theta over 3. Turns out this is impossible as well. And look at your reading in your ebook, and it tells you who did it and when and all that kind of good stuff. But remember, the important thing is that this has to be true for any angle. Yeah, I can take a right angle and I can trisect it. I could trisect a 45-degree angle. There are certain angles that you can trisect. Can you trisect any angle? No. And it doesn't just mean any acute angle. This means any obtuse angle as well. It's easy to trisect a straight angle. Straight angle is 180 degrees. I can make 60-degree angles out of that. But to do one with any single angle that you draw, nope, it's impossible. Okay, these are the 3 problems of antiquity. 1, 2, 3. Squaring a cube, squaring a circle, duplicating a cube, and trisecting an angle. And one of the things that's important with each of these is to look at what are you given and what are you trying to get. So in the first one, I am given a circle with a particular radius. Second one, I am given a square with a particular side length. In the third one, I am given an angle of any measure. Okay. All right. So that's the second big topic. I guess that's the third big topic here. So the fourth one is actually the third person we're going to talk about, Pythagoras, the most famous of all of these, maybe the most famous of all mathematicians. Certainly, I would say probably certainly, he came up with the theorem, or the theorem is attributed to him that more people know than any other theorem. Pythagoras, also a philosopher, almost a cult leader. I mean, he was a leader of a group of people known as the Pythagoreans. And their motto, their mantra, was all is number. Everything could be explained in terms of number. It all comes back to mathematics. Geometry does, all of math, algebra would, it all boils down to number. And by number, he means whole numbers. So when he looks at fractions, he thinks about fractions not as new numbers, but fractions are ratios of one whole number to another whole number. So everything here is in terms of whole numbers. That's a big deal. All right, the figure-it numbers. Now, this is the one place where I do want to go to our PowerPoint. So let me share the screen. Go here and go away. All right. When they said that all is number, they used numbers in lots of different ways, and they thought that numbers could be used to explain a lot of phenomenon. They also represented different numbers in different ways. So they thought of whole numbers as either odd or even. Well, that's one of the first ways that we think about to describe numbers. So they separated them by odd and even numbers. And they would represent an even number as a number that if you took that many pebbles and you put them down in 2 rows, you've got the same number of pebbles in each row. Can't get my fingers to line up. An odd number would have an extra one in one of those rows. But triangular numbers, square numbers, pentagonal numbers, those are numbers where you take the pebbles and you arrange them in triangles, squares, and pentagonals. Oblong numbers are sometimes called rectangular numbers. So they are numbers like 12 is 3 times 4. You could represent that as a rectangle of 4 rows with 3 pebbles in each row. Okay, so let's look at those triangular numbers, square numbers, and pentagonal numbers. So the triangular numbers would look like this. You would start with 1 pebble in that top row. That's the first triangular number. Then if I add 2 pebbles to the next row, I've got a new triangle made out of 3 pebbles. 3 is the next triangular number. Keep that one, but add 3 more pebbles. 6 is the next triangular number. Add 4 more pebbles, you've got 6 triangular numbers. All right, let me come back over here. I am going to make a table where N is just going to keep track of which number I'm talking about. First one, second one, third one, fourth one, fifth one. So T sub N is my column with my triangular numbers. So the first one is 1. The second one we saw was 3, and then 6. 10 is the fourth one. So take just a second and think about what's this next one going to be. Probably won't take you long to figure out what that next number is, and you might notice it in 2 different ways. You might see this as, well, I'm looking at how did I get from 1 to 3? I added 2. How did I get from 3 to 6? I added 3. How did I get from 6 to 10? I added 4. So to get from 10 to the next one, I'm going to add 5, and that's 15. Well, did you notice that that 5 was right there? 6 plus 4 gives you 10. 3 plus 3 gives you 6. 1 plus 2 gives you 3. So a couple of different ways of seeing that. And one way to represent this column generically is T sub N equals the previous triangular number. So that would be T sub N minus 1. I wrote plus 1. T sub N equals T sub N plus N, the current N that I'm talking about. So this needs to be minus 1. So the 5th triangular number is the 4th triangular number plus 5. The 4th triangular number is the 3rd one plus 4. This is a recursive definition. So if I want the 100th one, the 100th triangular number, I need to know what the 99th one is plus 100. I'm just going to add 100 to it. But to get the 99th one, I need to know the 98th one. And to get the 98th one, I need to know the 97th one, and so on and so on. Would be nice if I could just jump right to the 100th one. All right, we're going to come back to that. Okay, let's go back and look at the square numbers. All right, those are my triangular numbers. They're all shaped like triangles. They build on top of each other. Here are the square numbers. So start with 1 down in that bottom left-hand corner. That's my first square number. And then I'm going to build onto it. I'm going to add 3 more to get the next square number, which is 4. That's not surprising, 2 squared. I'm going to keep that corner and I'm going to add on to it. I'm going to add 5 and I get 9, the next square number. Then I add 7. I get the next square number, 16. All right, let me go back to my table and fill these numbers in. 1, 4, 9, 16. Oops, I didn't mean to. Oh, well, I'm ready to go back to there. So now let me fill in this column. S sub n, first one was 1, and then 4, and then 9, and then 16. What's going to come next? I bet you wrote down 25. 25 is one that maybe you thought of in two different ways. Some of you might have said, oh, it's 25 because that's 5 squared. Some of you might have said, oh, I noticed we were adding 3, then 5, then 7, so I'll add 9 to get the next one. All right. Well, that's interesting. I added 3 and then 5 and then 9. So I've got two different ways I could represent this number. One way, my S sub n. One thing I could do is say S sub n is n squared. Then to get S sub 100, oh, it's just 100 squared, it's 10,000. Well, this is a closed definition. Sometimes called a closed formula. But a recursive definition, well, I could do that too, because I said to get the nth one, I just take my S sub n minus 1 and I add an odd number. Now, which odd number am I going to add? When I was getting 25, I added 9, and this is my fifth number, so that's 9 is 1 less than 10. Here I added 7, well, that's 1 less than 8. Here I added 5, that's 1 less than 6. So another way to write this would be the odd number, which is 2n minus 1. So S sub 5 is S sub 4, which is 16, plus 2 times 5 minus 1 is 9. Sure enough, 16 plus 9 gives me 25. All right, I've got two different ways to write that. One of those is recursive, and one of those is closed. Let's look at the pentagonal numbers. I'll bet I can figure out some of these even before I go back to my pictures. What's the first pentagonal number all the way across there? It's always 1. So I'll bet if I even did my hexagonal numbers, and I don't have a picture for those, that would be 1. Look at the pattern on the second row. 2, 3, 4. Well, gee, I'll bet the next pentagonal number is 5. Well, doesn't that make sense? Pentagonal, pentagon, 5 sides. Hexagonal would be 6. That sounds reasonable. Hexagonal, hexagon, 6 sides. What about down here? 3, 6, 9. I'll bet it's 12. And if I follow that pattern, I'll bet that's a 15. Look at the next row. 4, 10, 16. I added 6 every time. So that looks like it would be 18. And maybe add 6 there would be 24. Well, let's go back and see. Let's come back over here. And share this. All right, there's my first pentagonal number. There's the next one. 1, 2, 3, 4, 5 dots. Here comes the next one. Now it's 1, 2, 3, 4, 5, but then come back out and add some more. So add 6, 7, 8, 9, 10. Wait a minute. 5, 6, 7, 8, 9, 10, 11, 12. Sure enough, I got 12 dots in that next pentagonal number. All right, there's 12. Keep going. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Oh, do you see what I did wrong in my table? I do. This, I didn't do the pattern here. I was still adding 3. So if I go back to my table, I'm adding 6 here. 6 plus 16 is 22. 6 plus 28 is going to make that 28. Add 3 every time here. Yeah, that looks right. Okay, now the question is, can I make recursive formulas and closed formulas for each one of these? And sure I can. I got that 22 by adding 12 and 10. Well, where did the 10 come? 12 plus 10. There's the 10. So the 12 is 5 plus 7. 4 plus 3 is 7. 12 is, wait a minute, let me add these up. Where's my 5? Then my 12, then my 22. So where's that 6 plus 16? There we go. There's the pattern. 6 plus 16 gives me my 22. 3 plus this 9 gives me my 12. 1 plus this 4 gives me my 5. And so on and so on. All right, now let me tell you something. This closed definition, the closed definition for each one of these columns is a quadratic equation. So the closed definition or the closed formula for the P sub n's is going to look like some quadratic formula Same thing for the triangular numbers, same thing for the hexagonal numbers. You just need to figure out what A, B, and C are. And you would get that by substituting in 1 for n, and P sub 1 is going to be 1. So substitute n for 1, substitute 1 in for n, and then 1 in for P sub n, and you'll get 1 equals A plus B plus C. All right, come down and let n be 2. Well, I've got 4A plus 2B plus C equals my second pentactagonal number, which is 5. 4A plus 2B plus C equals 5. Then let n be 3. 9A plus 3n plus C equals 12. That's 3 equations with 3 unknowns. I can solve those and figure it out. And you can check it out. Do the same thing for the triangular numbers, and what you'll find is that the closed formula for the pentagonal numbers is n times n plus 1 over 2, which you could write as 1/2 times n squared plus 1/2 times n plus 0. And after you do a couple of these, after you do T sub n and n squared and S sub n, P sub n, you will start to see a pattern in the formulas. This table is just full of patterns. There are so many ways to figure out how you get these numbers. And you can keep on going. The heptagonal numbers, octagonal numbers, and so on and so on. Okay. Now, let me go back. The other thing we know about Pythagoras is the Pythagorean theorem. And I'm going to work on that in just a minute. Here's my right triangle. Let me go back over here to our PowerPoint because I just want to point out the statement of the theorem where it's nice and big. All right, here we go. Here's what we know so well. In a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. That is the statement of the Pythagorean theorem. A squared plus B squared equals C squared. That's not the statement of the theorem because you didn't tell me what A, B, and C are. Now, if you want to say that in a right triangle whose leg lengths are A and B, and the length of the hypotenuse is C, then A squared plus B squared equals C squared. That works. That's fine. But the statement of the Pythagorean theorem needs to let you know what A, B, and C are, not just A squared plus B squared equals C squared. Okay. And you need to make sure that you say the legs are A and B. Those are the sides associated with the right angle. You need to say C is the length of the hypotenuse. Okay. That's the side opposite the right angle. So this figure that you see on this PowerPoint page just shows you the right triangle. You always start with the right triangle. I'm starting with the right triangle. And then if I were to draw a square off of each side, The squares off the two legs could be made to form the square on the hypotenuse. Okay, there are tons of different proofs of this triangle, of this theorem. And we're going to look at just one of those. And so I am starting with the right triangle. Here's my right angle. I'm going to label this side A and this side B and this side C. The PowerPoint has three different theorems, three different proofs in it, or setups for the proofs. So I'm going to do one of these. And so I think this is the first one. So I'm going to start by taking this triangle and I'm just going to trace it. And label the sides. So this is A and this is B and this is C. C is the hypotenuse. You're going to have some problems in your homework where you use the Pythagorean theorem to find side lengths and things like that. Now, suppose I take this side up here. Oh, let's see if I can do it so I can see pretty well. Take that side up there and I'm just going to extend that line straight out. Okay, just draw that line straight out. Then I'm going to take my right triangle and I'm going to turn it so that now my right angle is up here in the top right hand corner. And I'm going to place it so this vertex now on my original triangle is next to the other non-right triangle vertex. All right, let me trace that. I already got one of the sides, so just trace the other two. And label my sides. There's my right angle. Let's see, this one is A, this one's B, this one's C. Okay, let's extend this side. Now you're doing this while I'm doing it. So you just pause this PowerPoint while you make your own drawings. So I hope you paused and made up your own triangle to start with. I'm going to turn my triangle one more time. Now the right angle is in the bottom left-hand corner. Trace the right triangle. Label everything. This is A, this is B, this is C. And extend this side again. I've got three triangles here. I need to just draw one more. I'm going to draw one more, extend that side. Turn this triangle one last time. Trace these two sides. There's the hypotenuse. There's the other leg. And mark my right angle. A and B are the leg lengths. C is the hypotenuse. All right, so you do this for your triangle. So if we all do this, we've got 70 different triangles going on here. And what we're going to see is that this works for all of them. Now, depending on your triangle that you started with, some of you may have smaller squares in the middle than me. If these two side lengths are pretty close to each other, you've got a fairly small square in the middle. If you started with an isosceles right triangle so that A and B are the same length, you don't have a square in the middle at all. Or if you do, it's just a dot. All right, now here's the thing. This is an informal proof. And what we're going to do is find the area of this big square. Area of big square in two different ways. Well, it doesn't matter how I find the area of that square. The area of the square is not going to change. So finding it in two different ways, I'm still going to get the same area. So one way to look at it is it's one big old square. Another way to look at it is that it's 4 triangles and a square. Now, don't forget, I'm talking about the area of this stuff. All right, so when I look at this great big square, it's got 4 right angles. It's got straight sides. This side length is A plus B. This is A plus B. This is A plus B. This is A plus B. Yep, 4 right angles, 4 sides the same length. It's a big old square. Its area is the side length squared, which is A plus B squared. Make sure you put that A plus B in parentheses because we're going to do some algebra in just a minute. All right, area of 4 triangles. Well, all 4 of these triangles are congruent. They are all the same triangle. They are all right triangles. Base, I could call it A is in each one of them. The height is B. Area of a triangle is 1/2 times the base times the height. So that's A times B. Oh, but wait a minute. I've got 4 of those. So let me multiply that by 4. All right. Now, what about this guy in the middle? It's got all 4 sides the same length. How do I know that's a right triangle? Well, I'm going to pull something out that we haven't talked about yet, but that we know to show you that that's a right triangle. What are the 3? What's the measure? The measures of these 3 angles add up to 180 degrees. There's 90 degrees. So this triangle has these 2 angles whose measures add up to 90 degrees. Well, at this corner right here, that one and that one, those are the 2 angles we're talking about. They add up to 90, which means all 3 of these have to add up to 180, which means that has to be 90. These 2 are 90. That has to be 90 to make the total 180 degrees. So, yep, I've got a square, sure enough. So the area of this square is its side length squared. Side length is C, so that's plus C squared. So let's do the algebra here. Multiply out on the left-hand side, I get A squared plus my middle term is 2AB plus B squared equals 4 times 1/2 is 2AB plus C squared. And if I subtract 2AB from each side, I get A squared plus B squared equals C squared. I'll be darned. I get that the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. Wow. Pretty cool. In your PowerPoint, oh, didn't mean to do that. In your PowerPoint, you've actually got, share it, 3 proofs, or at least the start of 3 proofs. There's one of them. Now that's not the one we just did. There's the one we just did. Okay. And that takes you through it. So this one, what you would do is start with the triangle that you drew and let this hypotenuse be the length of each side of the square that you draw. Okay. The third one's different because you don't use a square, you end up with a trapezoid. So take the very same triangle that you've been using, but you're going to make a trapezoid. One of the things that's interesting about this proof is this is the proof that one of our presidents came up with. President James Garfield actually was the originator of this proof. And like I said, there are tons of different proofs of this Pythagorean theorem. There's a book in the library, if you want to check it out, that has, I don't know, something like 100 different proofs of it. So Oh, didn't mean to do that either. All right, so this will take you through this module number 4 on early Greek mathematics. And make sure when you finish this, you do the reading, make sure you do the homework first, and then make sure that you've got that homework done before you do the quiz and then do the reading quiz. Okay. On the homework quiz, there's one problem where it's not it's not tricky. Just be very careful when it talks about when you're walking out a door and you're going to turn east and west. Draw a picture. That's going to help you. When you draw your picture, draw your house. North is up, make south down, east and west, left and right. Okay. All right. Well, y'all be good. Have a good afternoon. I am going to go ahead while the dogs are quiet, try to get this next one done. See you soon.